Welcome to Lesson 8.4, Managing Database Security. In your Candidate Information Bulletin, we are in the Software Development Security domain. We are in Key Area of Knowledge E, which is Assess and Mitigate Vulnerabilities of Security Architecture, Designs, and Solutions. Our topics are going to include database management systems, concurrency and commit operations, online transaction processing, rollbacks, checkpoints, and save points, the ACID model, access control, data aggregation, warehousing, mining, inference, and injection. So a database management system, referred to as a DBMS, is a collection of tools that are used to administer a database. A database management system can be configured to meet the following security objectives. The first is integrity, that the state of the database is the same after a transaction has occurred as it was prior to a transaction. The second objective is availability, that in the event of a failure, the data should be available in its original state. The third is confidentiality, which is ensuring that data is available only to authorized users and objects. And the fourth is privacy, which is constraining data disclosure. So integrity, availability, confidentiality, and privacy. So we're going to look at the ways that a DBMS can ensure, again, integrity, availability, confidentiality, and privacy. So our first integrity control deals with concurrency. Concurrency issues arrive when a database is simultaneously accessed by subjects and other objects or other subjects. So database software should perform three types of integrity services. Semantic integrity mechanisms make sure structural and semantic rules are enforced, including deadlocking. Now, semantic mechanisms include data types, logical values, uniqueness constraints, and operations that could affect the structure of the database. Deadlocking ensures that we're not making two simultaneous changes to the same record. Referential integrity mechanisms ensure that no foreign key contains a reference to a null value or primary key of a non-existent record. And entity integrity ensures that tuples, that's just another word for records, are uniquely identified by a primary key. Commit operations also ensure integrity. A commit operation protects the integrity of data by ensuring consistency. So a commit operation will complete a transaction, execute the changes, and make available the changed environment. Those are the three components of a commit operation: complete the transaction, execute the change, and make available the changed environment. A two-phase commit operation is used when there are multiple databases involved. What a two-phase commit operation does is store the changes temporarily. The transaction monitor will send out a pre-commit command to the databases. If all the databases respond affirmatively, then the transaction monitor will issue a commit command, which will be executed by each one of the databases. At that point, we're back up to our commit operation, which completes the transaction, executes the changes, and makes available the changed operation. Now, online transaction processing also has to enforce integrity. Now, online transaction processing, also known as OLTP, is generally used when the databases are clustered to provide false tolerance and faster performance. Now, online transactions happen in real time, and updates need to be made across a distributed environment. So this complexity introduces additional integrity threats that have to be addressed. Online transaction processing should be designed in accordance with the ACID model in order to ensure integrity. So let's look through the ACID model. A well-written transaction code has four characteristics. We're going to look at the A, the C, the I, and the D. Atomicity means the transactions must be implemented in its entirety or must be completely rolled back. Either the transaction has to completely form or it's got to be completely rolled back. That's our A. Our C is consistency, meaning the transaction must be correct across all instances. So if we have multiple databases involved, the transaction has to be correct across all of the instances. The I is isolation, meaning the transaction does not interact with any other transactions until it's completed. The D is durability, meaning that after a transaction has been committed, it cannot be rolled back. Now, if there's a problem with the transaction or an error, errors need to be corrected by subsequent transactions, because once it's been committed, it can't be rolled back. So if you kind of think through these characteristics, our rules are transactions must be implemented in its entirety or completely rolled back, so we don't have sort of a half-formed transaction out there. Consistency, the transactions have to be correct across all instances, so everything's in balance. Isolation, that the transaction doesn't interact with other transactions until completed. And durability, that once it's completed, we don't roll it back, and that we correct any errors with subsequent transactions. Rollbacks are one of the techniques to ensure availability. A rollback ensures that if a transaction glitch happens, the database remains intact. Now remember, if we do a rollback, we've got to roll it all the way back to the beginning, and a rollback cannot be done after a commit operation is completed. So the rollback is an operation that either ends a corrupt or an invalid transaction, cancels the changes to the database, and logs the error. So it rolls it all the way back to the beginning. Checkpoints and save points are also availability techniques. Checkpoints and save points assure that if a processing error or a system failure occurs, the database can be returned to an earlier state. So this is not specific to a transaction. Really what we're talking about here is the database in its entirety. Checkpoints are a known good point from which the database can recover. The checkpoint process writes the current in-memory modified pages and transaction log information to disk and records information about the transaction log. So recovery to checkpoints are generally automatic. Save points are temporary backup files that can be configured based on a number of variables, such as time interval, user action, number of changes made, and a number of transactions. It's really an automatic backup, if you will. Returning to save points is usually a manual operation. And then we have access controls for confidentiality. And many of these access controls we're going to talk about should look very familiar to you. The database access controls can be designed to ensure that only subjects with a need to know, so again the need to know we've been talking about all through this course, can access data, and that their level of access is based on the principle of least privilege. So once again, need to know and least privilege. Content access controls can be enforced, and those are based on the sensitivity of the data. Context access controls can be enforced, and those are based on what the subject does or subject actions. Cell suppression is a technique that can be used to hide specific cells in the database. And database views are used to permit, allow, or restrict users or groups from viewing specific fields or records. So content access controls we looked at earlier, as well as context. Cell suppression, again, sort of unique to databases, or we might find them in a spreadsheet as well. And database views are used to permit, allow, or restrict users and groups from viewing specific fields or records. So those are access controls for confidentiality. Lastly, we need to be concerned with privacy. And those privacy concerns are really related to data warehousing, mining, aggregation, and inference, which are topics that we've previously discussed and we want to revisit. So remember that data warehousing combines data from multiple sources into a large database, generally with the purpose of extensive retrieval and trend analysis. Data mining is a process of analyzing the warehouse with tools that look for trends, correlations, or anomalies, resulting in metadata. Now, metadata is data about data, and as we've talked about before, can be more valuable and revealing than its original components. So when we start putting all of these pieces together, we can extract information which can result in a violation of privacy. Data aggregation is when individual pieces of data are combined and they create a bigger picture. And just like metadata, the combined information could have a greater sensitivity then the individual parts. This could also be a privacy violation. And if you think back to our privacy principles many, many lessons ago, one of the principles was that we should always let users know why we're collecting their data and how we're going to use it. But once we move into data warehousing, data mining, data aggregation, all of a sudden we open up this can of worms of all kinds of new ways that their data may not be used, that the user may not have agreed to, which in effect is a direct violation of privacy. Inference is the ability to derive information that's not explicitly available. Again, another potential privacy violation. An injection attack can lead to unauthorized access. Remember, as we've talked about earlier, injection is when a front-end system allows an unauthorized query or code to be sent to and executed. In this case, it would be sent to or executed in a database. And generally, the outcome of an injection attack, and I'm sure you've heard of SQL injection, is to extract information from a database or to be able to view information in a database. Certainly, unauthorized access is a violation of confidentiality and privacy. So as we've discussed earlier, input validation can prevent injection attacks. So in Lesson 8.4, we've looked at a database in terms of integrity, confidentiality, availability, and privacy. We discussed the components of a database management system, the issues of concurrency, of commit operations, of online transaction processing, and the need to implement the ACID model. We looked at rollbacks, checkpoints, and save points for availability, access controls, data aggregation, warehousing, mining, and inference as it relates to privacy, and then our concerns about injection and unauthorized access. That brings us to Lesson 8.4, Match the Meaning. Our terms on the left-hand side: a commit operation, a rollback, atomicity, aggregation, inference, data warehousing, and metadata. So I'd like you to put me on pause, take a few minutes, match the terms and the meanings from the left-hand side and the right-hand side. When you're ready, come on back and we'll go through them together. Okay, let's go through our Lesson 8.4 terms. A commit operation finalizes a transaction. A rollback reverses an invalid or corrupt transaction, taking it all the way back as if it never occurred. Atomicity is when a transaction is completed in its entirety. Aggregation is when we combine data to make a bigger picture. Inference is when we derive information from information. Data warehousing is when we combine data from multiple sources. And metadata is data about data. So that brings us to our CISSP exam tips. The first one is remembering that concurrency issues can arise when a database is being simultaneously accessed by subjects and other objects. Data warehousing can result in combining information that violates privacy, and that metadata can be more valuable and revealing than the original components. So thanks for joining me for this lesson, and I look forward to seeing you in the next.